Welcome Calculus 3 students. We are looking at Green's theorems today. Green's theorems are typically a way to make our lives easier in finding circulation or flux or something of that form. Notice that it will be a double integral, and I will find the two partials, and I will integrate that with respect to area. Our C must be a simple, closed, smooth curve oriented counterclockwise, and it must enclose a connected and simply connected region in R. Once we have that, then we know that we can use Green's theorem. In example 1, I'm going to find the circulation of a rotational field, and we did this example in section 15.2. So what we're going to do now is just confirm that we get the exact same answer that we did before. We will also use the definition of a two-dimensional curl right here and what that equals. So in order to find circulation, we are going to need to know the partial of G with respect to X, and we're going to need to know the partial of F with respect to Y. So let's look at our function f, which this is f and this is g. So the partial of g with respect to x is 1. The partial of f with respect to y is -1. I'm going to perform this double integral on this from on this space, and I will get that this goes from 1 and minus my -1 and then dA. This is just going to be my area of my R. So the area of this circle of radius 1 is then going to be 2 times that circle of radius 1. So this will end up being the area of my R is just going to be pi. So, oops, so I don't guess I have to do anything. There it is. Okay. In example 2, we are noting that the area of a plane is going to be given as such, and then they ask me to find the area of an ellipse. I can write this in terms of t as such, where t goes from 0 to 2 pi. Now note that I'm going to need to find out what x dy is, so let's just find out x dy, and I want all of this in terms of t. So I'm going to compute this quantity here. So x, that is a cosine t, dy is going to be then b cosine t minus y, that's b sine t, dx is going to be minus a sine t. And doing a little bit of trig gymnastics, you're going to get a b dt, because you're going to have a cosine squared plus sine squared is going to be 1. So now my area, in plugging into my integral here, is going to be this 1/2 integral of from 0 to 2 pi of this AB, which is a constant, dt, and performing this integration, you're going to get pi AB. Alright, now we have already calculated the outward flux of this radial field and found it in section 15.2. We found that this equaled 2 pi. So now we're going to note that we have our f function as x and our g function as y. Therefore, when I go to find the partials here, as what they ask us to do there, plus partial of g with respect to y, it's going to be 1 plus 1, which is equal to 2. Therefore, when I find this flux, it is just going to be the double integral over this region, and it's going to be 2 dA, and the area of this r, and it is a circle of radius 1, is once again equal to 2 pi. On this next one, we're supposed to evaluate this integral. Notice that this is given then as my f, this is given as my g, and I am doing this on a disk of radius 2. So what I'm going to do is compute this integral over my region, and my derivative of f with respect to x is then going to be 12x squared plus the derivative of my g with respect to y is going to then be 12y squared, and all of this over that area. That area is then, I'm going to change this to polar coordinates, so I'm going to have a dr d theta. My radius goes from 0 to 2 as noted here, which then means my theta goes from 0 to 2 pi, and this would be my pull out the 12, and I can see that it is a circle, so that's just going to be 12r squared, and remember I need an r here when I change to polar coordinates. Computing this integral and using those limits, you'll end up with 96 pi. In this next example, I am to compute the circulation. Now notice that my circles in this case go from 3 to 1 here. So there's my outside radius 3 and my inside radius of 1. In computing this integral, I'm going to need, over my region, this derivative here with respect to, first up it'll be g, because this curve is running counterclockwise on the outer semicircle but clockwise on the inner semicircle, so I'm going to have to swap this order, and I'll take the derivative of g with respect to x, so that'll be 2x, and then there'll be a minus the 2y, which is the derivative of f with respect to y. So changing that up just a little bit just to be able to integrate this thing. I'm also going to change this to polar coordinates, where my x is equal to r cosine theta, of course, and y is going to be equal to r sine theta. In changing those limits, I am going to have this r dr d theta whenever I change to polar coordinates. Notice that my radius runs from 1 to 3, and then my theta, since it's a semicircle, only goes from 0 to pi, and I would be writing this as 2 and then r cosine theta, r sine theta. And then I'll perform this integration, and after you perform that double integral, you should get negative 104 over 3 as your answer. I'm going to find this outward flux. I've written down my f and then my g. This one goes in that counterclockwise direction. Everything is working nicely here, so I am going to substitute in for f and g, and finding those partials, I will get, over my region, I'm going to take the derivative of f with respect to x, and that will get me y squared plus, and then my g, I'll take the derivative of this with respect to y, and I'll get x squared, and this is integrated over that area, and this will be my r dr d theta because I'd like to use polar coordinates here. Let's look at our boundaries. They go ahead and give us our r. That goes from 1 to 2. Very nice of them to do that for us. And my theta goes from 0 to 2 pi. And I just have a plain old r squared in here, which is nice because that's how that converts. In computing this integral, you should get 15 pi over 2. And that concludes all of the examples for this section. Included in your instructor notes are a summary of the different properties associated with these vector fields.